All right, welcome. These are the absolute last notes for college algebra, and they are again pretty relevant. Talking about exponential growth, which you guys saw in that video that we went over last Zoom meeting. What the cases are looking like for coronavirus, unfortunately. So that's why we're learning this, right? I know it seems like, oh, we're just learning because you want us to stay busy and you want us to focus on this test. No, I want you guys to grow and I want your brains to grow so that when you guys are the future of this country, you don't let something like this happen again. You allow science and research and other things to make your judgment and don't rely on hearsay and your gut, right? So that's a problem. That's why we're in this mess. I want you guys to change and make things better, right? Change the world and make things better. So that's why we're learning this stuff here. So, laws for uninhibited growth and decay. So we have this formula here, and you're not going to. Before you'd have to memorize it. Now you don't have to memorize it, okay? But this formula is for growth, like population growth, uninhibited growth, like usually things that are determined in the lab, uh, bugs, things like that, bacteria, viruses. Now, n sub zero, that's the original amount, right? So that's like what you're starting with. At t equals 0, t is like, day 1, or like you could say week 1 or day 0, or however you want to say it, right? That's your starting point. Now, we use e for kind of a unique reason. So why use e? Okay, if you Google it, you'll see it's kind of neat that uh, if you look at these populations and you kind of keep track of them, they approach e, the natural number. It's kind of a neat way to look at it. So if you have the time, and you do, look it up and see why we use e for this. Okay, it's actually has to do with limits, right? So the limit as x approaches infinity, well, it turns out it goes to e, right? And this e is a very important number. K is your growth or decay rate. So it'll be rewritten as a percentage, and then you'll just have to change it to a decimal. And T is time. Okay. So this is our last thing, right? We're not going to go through all these notes, just the ones that are on the final. There are 2 questions on the final on these, so I want to make sure you guys prepare for them. So applying the law of uninhibited growth and decay, the size p of a certain insect population at time t in days obeys the function p of t equals 500 e to the 0.06 t. So 500, there you see that's your original amount, that's your starting point. E is always going to be there. 0.06, that's your growth rate. Okay, which would be, of course, 6%. And t is the amount after time. So to determine the number of insects at t equals 0 days, okay, or like right when you're starting, you're not even measuring anything, and you could say, well, that's p of 0 equals 500 e to the 0.06 times 0, which is p of 0 equals 500 e to the 0.0, just 0, and then p of 0 equals 500 times 1, which is 500, and I did all this work just to show like, hey, I knew the answer before we started because it's in the equation, so it's going to work out that way. All right, so what is the growth rate? Well, the growth rate is 0.06, but it's always expressed as a percentage, so it's 6%. That means that they're growing at 6% each day. What is the population after 10 days? So P of 10 is equal to 500 e to the 0.06 times 10. Okay, be careful how you put this in your calculator. You got to use parentheses around the entire thing, depending on what kind of calculator you have. Otherwise, it's going to read it as e to the 0.06 times 10. So you got to be really careful how you put things in your calculator. And just putting it all in my calculator, I get P of 10 is about 911.06 days, or 911. When will the insect population reach 500? All right, so again, being a well-rounded, educated student, reading is important, right? Just as important as math. So when is talking about time. I want to know the time when the population is 500. Okay, time when time it was not 500, 650. So when does it equal 650? All right, and so what this is saying is I know 650 is my goal. I also know I have this equation that I gave you that I have to use. So the only variable that I have is t. Well, unleash the power of logarithms. I got to isolate my exponential term, so I'm going to divide both sides by 500. And you know, you should keep it exact, right? Like a Math Excel sometimes asks you for the exact answer, um, but 1.3 is exact, because it does go into it, so it's fine. But sometimes you'll get these decimals, and you'll say like, well, I don't understand. I think I did everything right. Why am I getting the wrong answer? Because they want you to use the exact number. Okay, so 1.3 is equal to e to the 0.06t. And the true power of logarithms here, I'm going to take natural log of both sides. And this works out great for us because I can just get rid of the e here. So now I have the natural log of 1.3 is equal to 0.06t. And lastly, divide by both sides by 0.06. So t is equal to natural log of 1.3 divided by 0.06, which is about, that's the exact answer, 4.37 days. So after 4.37 days, the amount of the insect population will go up to 650 from the starting at 500. Now, when will it double? This is a really neat idea called doubling time. Um, and doubling time, you'll see like we'll do the first one together, but you'll see like, oh, well, it's always equal to this. And yes, so you'll see that when you do doubling time, you'll notice a pattern. So when will it double? Well, if it started at 500, that means that 1,000 is a doubling time, right? Or the twice as much. So 1,000 equals 500 e to the 0.06 t. And like I said, the pattern that will emerge from this is that every time they talk about doubling time, it's always going to be the exponent equal to 2. All right, and this is going to be kind of a neat pattern that we'll discover over time. So now, natural log again, because I have e, natural log of e to the 0.06t. This comes down. The true power of logarithms is unleashed. Natural log of 2 equals 0.06t. Divide by 0.06, 0.06. And so the exact answer is natural log of 2 over 0.06. Of course, like nobody talks like that. That's not going to make a lot of sense. So we're going to put it in our calculator, and we're going to get about 11.55 days, or 11 and a half days for the population to double. That's pretty crazy to think about. Okay, and this will be kind of the last problem that we're going to do, because half-life and is going to be something that we're going to talk about here, and you're going to see it on the final. Okay, so brace yourselves. Don't shed a tear for our last college algebra notes. Be happy the journey that you took. All right, so solving for growth rate. The population of a colony of mosquitoes obeys the law of uninhibited growth. If there are 1,000 mosquitoes initially and there are 1,200 after day 1, solve the following equations. So what we're really solving for is K. We got to find the growth rate. Right? And we're going to use some techniques that we've developed over years. So we know that it's 1,000 mosquitoes initially. So again, you don't have to memorize this, and especially now you don't have to memorize this, but know the formula. So for it's n of t equals n sub 0 of e to the kt. And what we're trying to find is k. So let's look at what we have. We know the original amount is 1,000. That color, 1,000. we know that E is always going to be involved. We don't know K. T equals N of T. N of T. N of T equals 1,000 E to the KT. And what else? The other thing we know is after 1 day, it's 1,200. So 1,200 equals 1,000 E to the K times 1. So really the only thing now that we don't know is K is what we're trying to find. And we're going to use that K to answer all the rest of the questions. Okay, so let's think about this. K times 1 is just K. So I have 1,200 is equal to 1,000 E to the K. Divide by 1,000. So now 1.2 is equal to E to the K. And look, it's the same thing as we've been doing. We take the natural log of both sides. And I get K is equal to the natural log of 1.2. All right, save it. We're going to use it to answer all the questions. In fact, don't even change this to a decimal approximation. It's better to keep it like this. I know it seems like it's like a lot of things to enter in your calculator, but you're going to get a much more exact answer. So now using this, we can answer the rest of these questions. What is the size of the colony after 2 days? Okay, well, this is N of 2 for 2 days. The original amount is 1,000. That's always going to be the same for this particular problem. E, now my K is the natural log of 1.2 times 2. Now when you put this all in your calculator, remember to use parentheses, right? Otherwise your calculator's not going to do this correctly. And you just enter this entire thing in your calculator. So N of 2 is about 1,439 mosquitoes. That doesn't seem that bad, right? They only grew up by 439, okay? But now here's like the scarier question is, when are there going to be 50,000 mosquitoes? How long until we get that number? Well, let's see. 50,000 is the time, how long, right? It's a measure of time, equals 1,000 E to the natural log of 1.2 times T. T is my unknown here. All right, so I'm going to divide both sides by 1,000, and I get 50 is equal to E of the natural log 1.2 times T. And everything's kind of the same. Once we get that K, they're all kind of the same problem. You're going to take the natural log of both sides. And I'm left with natural log of 50 is equal to the natural log of 1.2 times T. And the 100% correct exact answer is natural log of 50 over natural log of 1.2. But again, that doesn't really help us because that doesn't make sense to a person that doesn't understand math. So T is about 21.5 days. That means that after 21.5 days, if a colony starts with 1,000 mosquitoes, they're going to end with 50,000 mosquitoes. 50,000 mosquitoes. Okay. Last thing here. All right, I have to stop. It's at 14.